Okay, we're all present and accounted for. I'm here. So let's go ahead and get started. I posted the notes to the website, so if you want my handwritten version of them, complete first. You can go to the website and get them now. I even posted today's notes, so those copies that I'm holding here are up on the website already. I don't know if that might be useful to some of you, but they're there so that you can go back and review. The first, oh, I forgot about that. The first lecture video is also posted. Right now it's just in a Dropbox because I couldn't quite figure out how to post a video that big to YouTube. So I will figure that out at some point probably. But it's there. Probably not something that you're dying to relive. This first section of stuff is fairly dry. It's a lot of definitions, yeah? Did y'all read chapter 1? Yeah. I mean, we're just going to finish notes on chapter 1 today, so we can talk about that and ask questions. I'm going to try to get through everything, but we're going to be done with chapter 1 of Thorne and Blanford today, so that next week we can move on to special relativity. And that's when things start getting a little more interesting. I assume all of you have had special relativity, at least at an undergrad level, right? Lots of Lorentz factors all over the place, holes and barns and twin paradoxes. We will do it. How many of you have had special relativity from a geometric or tensorial algebra perspective? Okay, good. Okay, so about half the class or so. So this might not be too unfamiliar to you. So after we do special relativity, we'll move on to translating that into general relativity. And we'll be done with Thorne and Blanford then in a couple more weeks. And then we'll hit the numerical stuff. We're building up to being able to solve these questions numerically. Okay, so let's get started with today's stuff. Any questions before we get started? Who could tell me, give me a definition for Euclidean space? I realized I used that term a lot last time. I'll use it more today. What does it mean? What is the bumper sticker definition of a Euclidean space? Flat. That is absolutely true. You could make it even simpler. What does it mean to be flat? So those two terms in my mind are actually sort of synonymous, right? And so I think you've just given it a different label. What does it mean, though?
Is it defined by the distance function being absolute value?
More or less, yes, exactly. So the bumper sticker version of what a Euclidean space is that the Pythagorean theorem applies. Okay, is that the Pythagorean theorem is correct. So if I've got some point A, some point B, and I make a triangle like this, and here's some point C, etc. The distance here, S, A to B, S, A to C, S, C to B, those distances are related to each other by the Pythagorean theorem. If this is true, if you go out and you're in some weird place and you're like, I don't know what's going on, I feel a little funny, I'm not sure if I'm in Euclidean space anymore, and you put down 3 points and you measure the distances between them in a right triangle kind of fashion, right? And this applies, well, then your space-time is flat. Your space is flat. I don't know about your time, right? So a Euclidean space, this is what I mean by that. And this is synonymous, right? This also implies that that the space-time is flat. The space is flat. It's not curved, right? If I were to do this on Earth's surface, would it be true? If I were to say Detroit to, well, I don't know, Grand Rapids to Flint, right? There's 3 points. If I measured the distances between them, if I got out, literally walked between, there was one of those little rolly things that measures distance, and just walked between those 3 cities in some right triangular, pretend it's a right triangle. Would the Pythagorean theorem apply?
No.
Why not?
Because you're on a sphere.
Oh, so the space is not flat, right? Now, now, what did I do in this room, right? Meet Alex, meet Halbert, right? And we made a right triangle somehow, right? What if I did it there?
It would be approximately.
But that, oh, I'm still on a curved surface, right? I'm on Earth's surface. What is?
It's very big.
What's very big?
The Earth.
The radius of curvature,
Yeah.
right? And so locally, it looks flat. And that's going to be a very important principle that we're going to use over and over again. Is that if I go small enough, even a curved surface looks flat, right? And that's an important principle that we use over and over. And that's why a lot of the stuff that we can develop for Euclidean spaces, we can translate somewhat easily into curved spaces. Okay, so let's keep going. So now, last time we talked about geometric-free geometric relations, right? Tensors and gradients and dot products. Now let's talk about a component representation of tensor algebra. Before we had no components. When you define the components of geometric objects like tensors and vectors, you are essentially then specifying a basis. You're specifying a coordinate in which you're working, right? Because otherwise components of a geometric object are not defined, right? It's just a vector. It's got a direction, it's got a magnitude. If I wanted to know what its components were, the components of that vector, I have to tell you, what am I measuring against, right? What's my x, y, and z, or what's my r, theta, phi, right? If I don't define what the coordinate system is, the concept of a component is undefined. It's just a geometric object in 3 space. Okay, so we can have a set of orthonormal basis vectors. Turn the page, turn the page. Something like what we're all very familiar with. Basis vector in the x direction, basis vector in the y direction, basis vector in the z direction, which is I'm going to define in my coordinate space as being the first, the second, and the third components of some basis vector. Okay? Now, since we're saying that this is orthonormal, these basis vectors have to be orthogonal to each other. And this implies that the dot product of any 2 of these basis vectors is what?
0.
Really?
Delta Kronecker.
Aha! The Kronecker delta. The way I've written it here, it would be delta IK, right? That's just orthogonality. That's just a definition, right? In 3 space, then, in component notation, having defined a coordinate system, I can write a vector as follows. Some vector A is just the components of that vector multiplied by the basis vectors. But see, before I had basis vectors, there were no components. In order to have components, I got to have basis vectors. I got to tell you where they're pointing, right? What am I measuring these components against? Same for a tensor. So for a tensor, something like, again, this is my, oops, starting to diverge, generic rank 3 tensor. It's got 3 slots for vectors because a tensor is a linear function of vectors. Here I can express this in component notation, T, I, J, K, and now I've got my basis vectors, and they are tensor product together. Again, before having defined a set of basis vectors, there were no components. Okay? So now, to actually get out what those components are, I insert the basis vectors into the tensor's slots.
and out comes my component. Which, if you actually specify all of them, if you specify I, j, and k as a scalar, it's a number. It's the component of that tensor. All right. And now, recall that we talked about the metric last time. Metric tensor, gjk. This is the tensor that gives us the inner product. If I insert the basis vectors into the metric tensor, I get, very conveniently, Kronecker delta, right? Because now I'm dotting, remember, the metric tensor generates the inner product. If I put the basis vectors into its slot, I get an inner product of basis vectors, which is delta function, right? That is almost legible in the video. Okay. We can build up. Again, this is just rehashing everything we talked about last time in component notation. We can now do the tensor product. Say I've got some rank 3 tensor, and I'm tensor producting that with some rank 2 tensor. In component notation, I could express this once I put in the basis vectors, and which I'm going to do that right now. So with this thing, I'm going to put in a set of basis vectors. I, j, k. Over here, e sub l, e sub m, like that. That thing, once I insert the basis vectors into the slots of this 5th ranked tensor, is just this. Oops. T, I, J, K, S, L, M. Much more compact notation. All right. And now the inner product in component notation. A dot B is simply AJ, BJ. Easy peasy. Where again, we're using the Einstein summation convention. Repeated indices imply summation. Similar for a tensor. I've got some tensor. I put in A, B, C into its 3 slots. That is T, I, J, K, A, I, B, J, C, K. Those tensors, those vectors go into the tensor slot, and we sum over each one of them respectively. Boom, got a scalar. All right. Some more machinery, tensor contraction. This is one that really benefits from a component representation because otherwise it's just, what? All right, so I'm going to say that the components of some 1 and 3 contraction of a tensor, so contracting on its 1st and 3rd slots, we're going to call this tensor just R, is equal to R, I, J, I, K. All right, so all of this messy gobbledygook that doesn't even look like math, you can represent in component notation by just this repeated indices in the 1st and 3rd slot. And since that implies summation, you get rid of those slots. And you take this 4th ranked tensor down to a 2nd ranked tensor. Contraction always reduces rank by 2. Okay. Now, so there's our component notation. All of this presumes that we have picked a set of basis vectors. and that they're orthonormal, right? Orthonormal basis vectors. Generally a Cartesian coordinate system, right? It's kind of clunky. It's kind of messy. And we would like a nice compact way to write geometric-free or geometry-free, coordinate-free geometric objects. So the book comes up with something which might be somewhat unfamiliar, which you've all read about. Slot naming index notation, which feels a bit like a bait and switch. Pulling the wool over your eye a little bit. But it is very convenient. So consider the case where we've got two tensors, G, A, B, and its slots. And this happens to be equal to some other tensor when I place the vectors into its slots reversed. Okay? If these were the same tensor, we might say that this tensor is symmetric. But imagine that they're different tensors, and if you happen to insert vectors in the slots reversed, they're equal to each other. Cool. How do you express this in component-free language, in coordinate-free language? It's very clunky, right? It's very hard to do that. One way you could do it is to name the slots in a coordinate-free way. So I'd have F, and now I'm going to say, okay, I got a slot. We're going to call you A. We're going to call you B. And then for G, I'm going to do something similar. I'm going to call this slot B, and I'm going to call this slot A. Well, that didn't really simplify our lives too much, did it? Now we're going to put labels on every single one of the slots, and where the vectors go in those different slots is kind of meaningful. It's kind of messy. So what if we just said, what if we just said the following, which was, let's take that hyper-expressive form of our tensor and just say this. Well, we just did that. That's a lot more compact. It's very convenient. But now it can be a bit confusing because this implies that we have components. It's an index notation, which implies components, which implies a basis vector, right? But now we're going to say, pretend it doesn't. Pretend that it represents this thing. Because if this is true, this thing here, it's true for all basis vectors, right? And so writing it this way doesn't change the meaning. It's a bit of a cheat, but it doesn't change the meaning. And so you will have to now, instead of writing things out in this very verbose way, when you use more compact slot naming index notation, you should indicate that you mean a coordinate-free object, not the components of some object in a coordinate system, right? That's all we have to do in order to make use of this more convenient nomenclature, in which case I can write that. And I can mean, using slot naming index notation, that this is true in all coordinate systems, that I have not specified a set of basis vectors, and that I'm not talking about the components, I'm talking about the geometric objects. Yeah?
So does this new FAB represent the linear function without inputs, or
Correct.
with A and B in it?
That's exactly right. So when we say slot naming index, we mean it represents the object without any vectors put into the slots. Yes, that is exactly the way to say it. And if we put vectors in those slots, for instance, basis vectors, we get components. You could put other vectors in those slots. They won't necessarily be the components of the tensor in some basis, but they'll give you a number. Okay, cool. This gives us a nice way to do things like contractions in a more clean notation. Okay. So now let's talk about contractions. Okay. So the components in some basis would be, so here's some 1,3 contraction of some object T, some tensor, is equal to TAB. Okay, so that would be the components. If I pick the basis and I stick the basis vectors into the slots, and then I contract on slots 1 and 3, this is what I'd get. Now, with slot naming notation, we're going to say that TABA represents the contraction itself, which is to say exactly what Mike said. Now I'm saying that TABA represents the contraction operation without basis vectors put into the slots. It's a convenience. But a convenient means I don't have to write this out anymore. And I can still use coordinate-free language. Make sense? Okay. All right. So let's revisit the example we used last time of particle kinetics. And we can write this out with our indices. And if I write this out in index notation, the velocity, dxi dt, just like that. The momentum, pi, a vector, is just the mass times that velocity vector. The acceleration vector is the derivative in time of the velocity vector, which is the double derivative of the trajectory. And the energy is the same thing. Where now I've repeated the indices, Vj, Vj, implying summation. Now, I can say, oh, one more. And so if this is the same particle kinetics that we were talking about before, where we've got electric and magnetic fields and some charged particle, then I have a force law. My change in momentum in time is charge of the particle. Electric field components, don't get confused here. This is the scalar energy. This is the electric field vector. I switched back to using the notation that the book uses. Eta ijk, Vj, Bk. Now we've introduced a new object here. What's this guy?
Levi-Civita tensor.
That's right, Levi-Civita, I think because it's Italian. But yes, the Levi-Civita tensor. And what does this do for us? What's it doing here in my index notation representation? It's giving me the cross product, right? Because we all know this, it's E plus V cross V, right? And so writing it out in notation, this is the way that I would write a cross product, okay? Is I make use of this Levi-Civita tensor, and we're about to get into more gory detail about Levi-Civita in a minute here. So it gives me the cross product in this particular case. It also denotes the sense of volume in my space. So the way that I have written this here, we can interpret this using either slot naming index notation or just component notation as either being the components of all of these geometric objects in a particular basis, Cartesian coordinates, or we could say that they actually represent the geometric objects themselves in a coordinate-free way. We can choose to say, have I filled my slots with the basis vectors or not? If I haven't, I'm using slot naming index notation. Looks exactly the same as this. And if I have put in my basis vectors, well, then these are components in a Cartesian orthonormal coordinate system. Cool. All right. So now let's talk about transformations. Orthogonal transformation. So we've done this. You've done this in mechanics. Very familiar with it. Rotation matrices and whatnot. So I can expand the bases of any Cartesian coordinate system with respect to any of it, right? You know this. We can make rotations and reflections and transformations. And so any set of orthonormal basis vectors can be represented by some other set of orthonormal basis vectors, all right? And what that means is that EI, P hat, R, P bar, that, and similarly, P bar is equal to EI, R, I, P bar. Okay, so both of these, E sub I and E sub P bar, are orthonormal basis vectors, but they're not the same orthonormal basis vectors. And in order to relate components of some object in one basis to the other, I need the use of this R thingamajig, which is not a tensor. It is a matrix, actually, right? Which is a different thing, right? So this is not a coordinate-free geometric object that the tensor is, which we've come to know. This is actually a matrix. It's a rotation matrix, right? Okay. This rotation matrix, let me just write that out. It's the rotation matrix. In fact, really what I should say is that it's the components, because now I put the little component notation on them. Specifically in this case, I mean these are the components of that matrix. To be very clear with my language, what I'm talking about there. All right, they're the inverse of each other, meaning R P bar I is equal to R I P bar. Oops, not what I meant to be. I mean, that's true, but what I meant to write is the following. This is the delta. Hold on. Writing too fast based on my notes. So R P bar I times R I Q bar is equal to the delta function P bar Q bar. Similarly, if I switch the index over which I'm summing, I can do this. I P bar times P bar J, well, that's just delta IJ. Okay. Now, we've already said that we're in an orthonormal basis, right? We've specified that. So orthonormality implies the following. This is just sort of our definition, is that the dot product of any of these basis vectors is equal to the delta function. But this also has to be equal to the following, which is E, P bar, and the rotation matrix. Because we've had that over here. Okay. Similarly, Q bar times R Q bar J is equal to R P bar I R Q bar J times the dot product of the basis vectors P bar dotted into Q bar, all of which is equal to R P bar I R Q bar J delta, p bar, q bar, and we're right back to where we were. R, p bar, I, R, p bar, J. We got that from specifying orthonormality, the top line, and this behavior of the rotation matrices. Which all of that is to argue that the rotation matrix itself, and here I'm using brackets to now represent that I'm talking about the matrix, not the components, is the inverse of this other matrix, R p bar I, cool, and that's also equal to the transpose of that matrix, R p bar I. So for this particular matrix, the transpose and the inverse are the same thing for the rotation matrix in an orthonormal basis. Okay? This further implies that R, whatever you want to pick for its components, is a rotation or reflection. Again, as we're used to from mechanics. Okay. All right, so let's use this for a minute, okay? So since geometric objects, like vectors and tensors, are coordinate free, right? They're basis independent, right? They don't change. In other words, this goes back to when I asked on Tuesday, like, what's the definition of a vector, right? It's something that transforms like a vector, right? It doesn't change under certain transformations, right? Another way of saying that is geometric objects like vectors and tensors are basis independent. Not their components, obviously. The components change, right? But the objects themselves are the same. That's one way of defining it, okay? We can say something like this. For some vector A, we can bust it up into its components in some basis E sub I. Because of our definition of the rotation matrix, we can express this, the components of A, and any other orthonormal basis, P bar, let's say, using the rotation matrix, where this rotation matrix takes this E sub P bar and makes it E sub I. That's what it does. Same deal. This then is equal to the rotation matrix P bar I times AI times E P hat. I'm just multiplying through. And this has got to be equal to A sub P bar. So now I've used the rotation matrix to take my components of this vector in some basis and give me new components in some other basis. That's what it does. That's what it does. Similarly, let's take a rank 3 tensor, do something like that. Gonna be a lot of bars in this one. Makes me thirsty. A little humor for you there. Okay, so there's a bunch of rotation matrices. So again, repeated indices imply summation. I apply these rotation matrices to some tensor, the components of some tensor, in this case ijk, and they give me the components of that tensor in some other basis, p bar, q bar, r bar. Okay? All right. Questions? Good, because this stuff's real dry. Let's move on to talking about directional derivatives. That's nice. All right. So this directional derivative. Who wants to give me a definition for a directional derivative? What would you say it is? I said, oh, what's the directional derivative?
Derivative in the direction of a vector.
It's like turn the words around. That's exactly what it is. You're just taking the derivative of something along some direction, right? If we did this along the orthonormal basis that we're used to, like in Cartesian coordinates, right? We just call it something the gradient, right? But you know, the gradient is actually a special case of a more general thing, which is the directional derivative, right? It's just there we specify that the directions that we want to take the derivatives along are the orthonormal bases of some Cartesian coordinate system, right? So I'd write this out as here. I've got my nabla vector A. That's the direction I'm taking the derivative. And here I'm going to do the usual Leibniz limiting function as some small thing goes to 0 of 1 over that small thing times the difference in that tensor at some location P plus epsilon A minus the values of that tensor at the original location xp. It's just, that's the definition of a derivative, right? But now what I've done is I've said that the location, the direction I am going to measure the change, I'm specifying by the vector A, right? This is a more general idea than the gradient. Again, it would just be the gradient if I stuck in the basis vectors. Okay. All right. A few notes about this. What's this do to the rank of the tensor? Nothing, right? The tensor rank is unchanged. Okay. It's also a linear function of A, the vector. Makes it sound like a tensor. So let's talk about another way to express this. So assume that I've got this tensor T, which is some rank n tensor field, by which I mean that the tensor varies in space, right? Different locations x, tensor can take on different values. And then let's let grad T be some other rank n plus 1 tensor field. Okay? So this implies that, relating back to my directional derivative in a more robust way, okay? 1, 2, 3, and here in this slot, I'm putting in A. Okay? So this is what I meant before by the directional derivative being a more general object, and by inserting A into the slot here. Okay, so the gradient operator took this tensor and increased its rank by 1. But by taking now the directional derivative, I'm taking the vector that I want to take the directional derivative along, and I'm inserting it into that new differentiation index, that new slot, and thereby reducing the rank by 1 again, right? So you get the same rank object. This is pretty familiar, right? Like if we were in a Cartesian orthonormal basis, and I had some just scalar field, you know, like a density or something like that. I said, okay, take the gradient of this scalar field. What would you get in terms of the rank of that object? Be a vector, right? You'd have some 3 components, right? You'd have the gradient in the x, gradient in the y, gradient in the z, right? And so you're very familiar with that, right? Gradients increase the rank of the object by 1. This directional derivative then, by inserting a vector into that last slot, reduces the rank once more. Okay? We'll call this the gradient, and this is then the differentiation slot. Okay, so in slot naming notation, we could represent this pretty easily. We're going to say that the tensor becomes the gradient, I meant to say, ABC semicolon D. That's how I'm going to represent the gradient. Anything following the semicolon is the index that I'm differentiating. Okay? Similar for the directional derivative. Now, in index notation, this is going to be T, A, B, C, semicolon J, A sub J. Where it's exactly this here, right? I'm taking a gradient, this part, and then I'm inserting a vector into that differentiation slot. And then repeated indices imply summation. I got rid of that index. Okay. Make sense? I think this notation is a bit clearer. Like you kind of get the feeling better for what do I mean by inserting a vector into its slot. I mean I'm taking a dot product. Essentially, right? I'm getting rid of that index by summing over it with the components of some other vector. But what I just said there assumed a coordinate system, right? Because I'm using components. So if we want to talk geometric free language, we have to be a bit more precise than that. That's essentially what I mean. Okay. So some important properties of the gradient and directional derivative. So they obey the usual commutation and chain rules, okay? They obey the rules that we're used to in calculus, right? So, for instance, directional derivative along A of some tensor S cross tensor product T is equal to the directional derivative of S tensor product T plus S tensor product directional derivative along A of T. Handy, right? We're used to that. In index notation, slot naming index notation, I could express this easily as SABTCDE, implying a rank 2 tensor and a rank 3 tensor. I didn't specify rank up there. All of that semicolon, I'm missing something there, semicolon, J, A, J. Okay? This is equal to S, A, B, semicolon, J. If you get confused, semicolons and J's right next to each other, super clear. I'm going to try to differentiate my J. If it is unclear, please stop me and ask. Okay? A, J times T, C, D, E plus S, A, B times T, C, D, E, semicolon, J, A, J in slot naming index notation. I think it would be more compact if I hadn't started writing bigger. Okay, so usual rule, commutation, right? And the chain rule. Okay. Other rule that we're going to use is the directional derivative here, f t, right? I'm multiplying by some scalar f. Directional derivative of that scalar field times the tensor t plus f directional derivative of the tensor. Easy. In slot naming index notation, that would just be f t a b c, all of that semicolon j a j, directional derivative, right, is equal to then f semicolon j. Now here I'm taking the gradient of the scalar field, right? That's what that means. Oops, now it's a directional derivative. T a b c plus, same deal, here's my scalar, T a b c semicolon j a j. Okay. Fun stuff. Questions? Let's talk about metric for a second. Okay. Other useful little bits of information. So in flat Cartesian, flat space, Cartesian coordinates, right, which is more or less what we've been using up to this point, the gradient of the metric disappears. All right, that's by definition. Another way of putting that is that in index notation, a, b, comma, j, 0. Okay. Another thing is that the contraction of the gradient of a vector gives you the divergence. You know that. I think I'm gonna have to switch. This is fading out. Everything's gonna turn blue. Okay. So we can represent that as divergence of some vector A is defined as the contraction of the gradient of A, which we can represent A sub A semicolon A. Okay, and similar for tensors. Okay. One last important thing. Okay. So now, if we take a double gradient, of some tensor, then contract that new object that we made on the two new slots of that tensor, right? Because by taking a double gradient, we've increased the rank by 2. Gradient, 1 rank, gradient, 2 ranks. And then we're going to contract on those 2 new slots. This gives you a little something we call the Laplacian. You guys ever thought about these? These are all very familiar to you, but have you probably not thought about them in these terms, right? So in other words, Laplacian of some tensor is defined as taking the double gradient of that tensor, like that. Or in index notation, T, A, B, C, semicolon J, J. Okay? Now again, as you read in the book, if I've got a semicolon or a comma, all of the indices following it are differentiation indices. So here, this notation implies that I'm taking the gradient twice, and since it's the same index, I'm summing that. Same thing. All right. Okay. So just to make that clear, so for another example, differentiation, we would say something like T, A, B, C, comma, J, K. Now, commas usually represent partial derivatives rather than the full derivative of a semicolon. We're going to define that to be partial squared T, A, B, C over partial X, J, partial X, K. Right? So the partial spatial derivatives in those 2 directions. And if they were the same, I'd derive back my Laplacian. Right? Because I would sum them over those indices. Okay. Yeah. Questions? Let's take a short break. 90 minutes is a long time for me. I'm not going to talk that whole time. Follow along. This is super dry stuff, I know. Have any of you started work on the problems? Fine if you haven't. Steve, stop. Good. How are they?
Not too bad.
Right? They're just kind of exercises, right? Applying this stuff.
The only tricky part is trying to figure out what they're asking in the field. At least I did one part of it was off the rotation matrix, and one way. I read the second part, I'm like, that's what I did. So I did something on one person, obviously.
Okay.
I read it wrong anyhow. I did the wrong thing.
You were just anticipating where they were going. Is there a water fountain up there? Yeah, there's water. Be right back. Okay, well, let's dive back in. That's enough of a break for me. Let's talk Levi-Civita. Okay. Okie dokie. So this little eta guy. So just like the metric Okay, the metric tensor embodies the sense of distance in some space, right? It generates the inner product. And so in some coordinate space, in some, in this case we're dealing with Euclidean, but it'll also apply in non-Euclidean spaces, it gives you the sense of distance between points in that space. The Levi-Civita tensor gives you the sense of volumes in that space, right? So going beyond just the tensor. So if I've got some, I'm going to draw a little dude here. And up like this. Connect them like that. So I've got something like this. So I can take these three vectors. It doesn't have to be a cube. This can be any general parallelepiped, right? Defined by three vectors meeting at some vertices, right? How I would define some general parallelepiped. Be any shape, doesn't matter. From this, I can use the Levi-Civita tensor to give me what the volume of this is by definition. So in this case, if I've got this guy right here, the volume of this parallelepiped is going to be defined to be the Levi-Civita tensor with those vectors plugged into its slots. So it defines the sense of volume in some space. It is not necessarily three-dimensional. It's not necessarily two-dimensional. It is arbitrarily dimensional. And so we'll call this the free volume, right? The in volume of some arbitrary parallelepiped it could be a hypercube or any hypergeometry object is going to be equal to the Levi-Civita tensor operating on the vectors that define the shape of that object up to some, who knows how big it is, right? Some set of vectors into the slots. I'm just going to abbreviate Levi-Civita as L-C. Is anti-symmetric. Okay, which means that if I plug the vectors in A, B, up to some F, this is actually equal to the negative of the other way. A, B, F. Anti-symmetric, right? Sign flip. And then its components for a right-handed orthonormal basis, okay? Right-handed. Orthonormal basis. Like that one. The components of the Levi-Civita tensor are as follows. Okay? Eta 1, 2, 3 plus 1. Eta A, B, C then is equal to plus 1 if A, B, C is an even permutation of 1, 2, 3. Even permutations, 1, 2, 3. It is equal to minus 1 if A, B, C, an odd permutation of 1, 2, 3. And it's equal to 0 if A, B, C, not all different. So if any two of the indices are the same, it's 0. Okay. So not only does the Levi-Civita tensor give us the sense of volume in some space, does the handy task of the eraser was black. Probably because of the eraser. Gives us the cross product and then ultimately the curl as well. So LC generates cross product. So the cross product of two vectors A and B is defined as the Levi-Civita tensor with A and B in its final two slots. What's the rank of this? 1. It's a vector, right? Cross product. And in slot naming index notation, I can say that this is equal to epsilon I j k a j b k, right? In slot naming. Similarly, for the curl of some vector A is defined to be epsilon I j k a k semicolon j. Now, I'm not writing this out in coordinate-free notation. I'm only using slot naming notation here because writing this out, like this expression in coordinate-free language, is kind of hairy, kind of ill-defined. But what this represents, just like when we were talking about gradients and directional derivatives before, this is a double contraction of a rank 5 tensor, all right? That rank 5 tensor being the Levi-Civita tensor product into the gradient of A. And then contracting on the 2nd and 5th slots, and then contracting again on the 3rd and 4th slots. That's what it is. That's the way you say it. The way you write that out, I don't know, but this is a heck of a lot easier because that's what it represents. Aditya.
Should it be a comma there? Because isn't the curl, isn't it like the difference of partial derivatives? You know, like in each component.
Yeah, I understand what you're asking. This is a good question. It could be a mistake in my notes. What I have written on my handwritten notes there is definitely a semicolon. But let me double check with what.
I think it'll be a comma in Cartesian. This is just supposed to be any coordinate basis.
This is any coordinate basis. That is true. And it's also true, and you read this in the book, is that in Cartesian, the comma and the semicolon are the same thing, right? That doesn't matter there. But the question is here, is what I have written correct? It's what they have in the notes. And so it is the full semicolon derivative. So I'm going to go with this. We can talk more about it later if that doesn't make sense. That's what I thought was right. Yeah.
Another question about the Levi-Civita tensors. I don't believe the book answered this, but what does it mean to have a negative volume?
Well, that's just a choice of sign, right? What does it mean to be negative or positive, right? It's all depending on your perspective. You know, why is north north and south south? Negative volume doesn't make a lot of physical sense in Euclidean 3 space. Like if I told you something had negative volume, talking about dark energy, what's going on here? But in the mathematical notation here, it really just is a choice of sign. It's going to matter a bit more when we start talking about space-time, what that sign is. And there, -4 volumes have a little bit more of physical meaning than a negative spatial volume, -3 volumes. That's here. It's just a choice of sign. Actually, let me describe this to you even better. So if I had a right-handed coordinate system, I think this will work. But we're doing it live. Let's see. Okay, so what if I said the following? So here's my thing, right? And I got the volume of this thing by doing a Levi-Civita tensor, right? And it was positive because this is a right-handed thing and things were pointed this way. But now, if C points that way, conversely, C would actually be out here, right? Because they need to have the same origin. If then those were my vectors defining my object, and I took the Levi-Civita tensor of that, sign flip, negative volume. It's just a choice, sign choice.
Okay.
Doesn't mean you've gone into the wormhole. Not yet. Other questions? Okay, so there's one more handy dandy thing about Levi-Civita. I'm going to put it here because that picture was useful, so let's keep it up for a minute. So in Euclidean 3-space, the following relationship applies, and that is eta ij m times eta k l m is equal to this 4D delta function. Okay? Delta ij on the top, kl on the bottom, which we are going to define as delta ik, usual Kronecker, delta jl minus delta il delta jk. And this is just a property of the Levi-Civita tensor in Euclidean 3-space. And here again, delta is the Kronecker delta. So for this thing to be non-zero, a couple of things have to be true. So for this to be not equal to 0, you got to have one of the two things, one of the two following. Either I has to be equal to k and j has to be equal to l, right? Which gives me 1 here, 0 there. Okay, and that would have positive sign, or I has to be equal to L and J has to be equal to K, and this would actually give you would have to have a negative sign on that. I think you're going to have to use that in one of the sign homeworks problems. Okay. All right. Now, the rest of class, what time does this class end? Does this class end in 5 minutes? Yes. Rats. Okay. Oh well. We can do it. I think we've talked sufficiently about that. You can use the Levi-Civita tensor to also get areas. Okay, so let's talk about this real quick. Shouldn't have gotten rid of my thing, but here's a 2D surface now defined by vectors A and B. All right, let's say that this 2 surface lives in a 3 space. I can then define some, here's the unit normal, n, vector n, to that surface. The surface has some area, confusingly I'm going to call A. In that case, I can define a vectorial surface, right? The sigma vector. That is sigma is equal to A cross B. Right, no problem. But now we've already said that we're going to use the Levi-Civita tensor to generate cross products. So this then gives me open slot there, A, B in the second two slots of the Levi-Civita tensor. And that's how I would do this. And in some sense, a vectorial surface area is a geometric object that's kind of looking for a third leg to make a volume, right? And so if I were to add another vector, C, from the same origin here to define an actual three-dimensional object in this space, I could stick that into the third slot and get a volume out, right? Because that's what the Levi-Civita tensor wants to give you. Fill up all its slots, you get a volume. Okay, we already sort of talked about negative volume a little bit. So I'm going to skip ahead. Some of these things we will come back to, so it's not a big deal if I get to it in the lecture. But I think this is kind of useful. So let's derive some conservation laws. Get back to physics a little bit. Okay, so particle and charge conservation. Now we won't start from Nader's theorem, but we'll do something fairly fundamental. Let's call this rho sub E the charge density, and N, as usual, the number density. Okay, then the conservation of these two things tells me the following. The time rate of change of the volume integral over some 3 volume of the charge density. So this thing is what? That's the total charge in the volume, right? Total charge in the volume. The time rate of change of that thing has got to be equal to the negative of the integral, over the surface that encloses that. So I'm saying partial V3. That means the 2 surface that encloses that 3 volume. It's a closed surface as well, by assumption, okay? J dot sigma, okay? This is the current density, right? So how much charge is flowing? This is the flow of charge. So what this says is that the flow of charge dotted into the surface area, right, the surface vector, then integrated over that entire surface gives me the total amount of charge that is moving out of that surface. All right? And if I get a positive value for this, meaning that charge is flowing out of that surface, the total amount of charge in my surface is decreasing. Easy peasy, right? You can just intuit that. So we usually then write the law of charge conservation to be that. Just bring it over to the other side. All right? So we're going to call that the law of charge conservation. So this is the time rate of change of the total charge. This is the net flux through the surface bounding the volume that I care about. That's it. Okay. We can pull this time derivative into the integral. That actually turns it into a partial derivative. And then we can use Gauss's law to change this surface integral into a volume integral, right? That's what Gauss's law does. Use that all the time. So then that gives me, we're now doing volume integrals. The volume integral of the partial derivative of the charge density with respect to time plus the divergence of the charge, what did I call that thing? Charge flux, but that's not the right word. The current density, integrated over the volume is 0. All right, so all I did was take this partial derivative inside the integral, uses Gauss's law to change this surface integral into a volume integral. And it's got to be the divergence of that thing by Gauss's law, okay? Now, if this is true, if the integral of this thing is equal to 0, the integral of all things that could possibly be in this integrand has to be 0, right? In other words, the integrand is 0. Always, for any volume. I haven't specified any coordinate systems here. I haven't specified anything. This is coordinate-free language, right? That integrand must be 0 if this is true, because it's a completely arbitrary control volume. And that gives me then what we're usually used to looking at for the differential conservation law, right? Well, in that case, I'm just going to cheat because we've only got a minute left. And I'm just going to say this. So I can turn that into that. Okay. The last thing, which I think I might hit on then Monday, just as a little one-off, is the stress tensor, because that's important. This is for charge density. You can then use the stress tensor to derive momentum conservation, because like this is the current density, it's the flux of charge. The stress tensor is the flux of momentum. And so if we care about momentum conservation, we can do exactly the same argument, but use the stress tensor instead and get a conservation law for momentum. The stress tensor will be an important object, so I didn't get to it today, but we'll hit it very quickly on Tuesday and then dive into special relativity. So for Tuesday, over the weekend, you got plenty of time, read chapter 2 of Thorne and Blandford, or Blandford and Thorne, depending which one you're looking at. They're the same, except the jokes. I do recommend that you take a look now at homework 1 and start playing around with the problems. We've got all the machinery to do that now. Okay, any other questions? We're over time a little bit again. All right, thanks, appreciate it.